This is a video about waves like we've been talking about in class, and also about the math that's associated with these waves. So it's long been established that light travels in waves in this manner. This is called a transverse wave as opposed to a sound wave, which travels like this. A sound wave is a longitudinal wave, so it goes back and forth like this. So a compression wave like that. But a light wave goes up and down, transverse wave. All right, a few key terms that are associated with waves. The distance right here is called the wavelength. And the number of times that the wave goes from top to bottom to top in this direction is called the frequency. So will remember the wave demo that I did in class with the spring that was tied to the cart, and we saw that as the wavelength got shorter, the frequency got larger, which means that wavelength and frequency are inversely proportional. So looking at a picture here, this is a picture of a transverse wave with changing wavelength. So you see as the wavelength gets shorter, this is 10 to the negative 12th meters, the frequency got higher, 10 to the positive 20th. So as one gets shorter, this is 1,000 meters, 100th of a meter, and so on, the frequency gets higher, 10 to the 4th hertz, 10 to the 8th, and so on. So wavelength and frequency are inversely proportional. All right, so we represent that, or represent the relationship between wavelength and frequency according to this equation. Where c stands for the speed of light, we're going to use 3.00 times 10 to the 8th meters per second. So the speed of light is a constant. It doesn't change. Technically that's a speed in a vacuum, but we treat it as a constant in these equations, just like pi is a constant in math equations. It's 3.14. This is wavelength. Wavelength is measured in meters, so wavelength, and then frequency is measured in, as I said, from top to bottom to top, the number of cycles per second. We usually talk about let me write down what the variables are called. That's the speed. This is the wavelength. And this is the frequency. Okay, wavelength measured in meters, frequency measured in cycles per second. We usually don't use the word cycle when we talk about frequency. We usually say that we can measure the frequency either in reciprocal seconds or in hertz. So 1 hertz is the same as a cycle per second, or a reciprocal second, 1 over s. Again, wavelength is meters and speeds in meters per second. These are Greek letters. That one's lambda. That one's nu, in U. All right. So in class today, we also talked about light traveling as particles. In last class, we talked about light traveling as particles also, and there's an equation that we use that deals with the energy of a particle of light. A particle of light is a photon of light. So we could say the energy of a photon of light is equal to h times frequency. All right, so E stands for energy. And energy is usually measured in joules. You remember joules from physics class. H is a constant. I'm going to put it down here because I need a little bit more room to write it. It's called Planck's constant. And its numerical value is 6.63 times 10 to the negative 34th joules per hertz. And this again is frequency. And frequency is either in reciprocal seconds or hertz. Reciprocal seconds tends to get used in that equation, but hertz is preferred in this equation. So you can measure it either way, but hertz is preferred in the E equals h nu equation. So really we have two kind of simple equations to deal with light. One treats light as a wave. So if you have a wavelength, you'd use this equation. One treats light as a particle. If you're talking about the energy of a particle, you'd use this equation. So let's take a look at a couple of problems. I'll look at one we worked on in class today. We'll just try this one out. So we have a certain violet light, has a wavelength of 413 nanometers. And so if we looked at a piece of light from the picture I showed you earlier, violet light would be, oops, bring this picture all the way in. There we go. Violet light would be in the visible spectrum, somewhere in here, and these are in meters. So 10 to the negative 7th meters is like 0.5 times 10 to the negative 6 will be 5 times 10 to the negative 7th. So you see that's in the range of visible light. So violet light would be a visible light. Now you might notice also that when we get up into the higher frequencies, light gets a little bit more dangerous. So when we get up past ultraviolet, these high frequency lights are harmful to us because they have more energy. So the higher the frequency, the more energy you have. All right, so we have violet light with 413 nanometers. Since the speed of light is given in meters per second, we would need to change our nanometers into meters most likely. So let's go ahead and do that. We'd have 413 nanometers. We know nanometers would go on the bottom of our conversion factor. We'd have meters on the top, and 1 meter is 1 times 10 to the 9th nanometers. So when you do that on a calculator, you need to use the EE button. So you'll end up with 413 times 1 and then divided by 1. Notice the EE or EXP. Mine has EXP on it. EXP to the 9th. And that equals 4.13 times 10 to the negative 7th. Notice I did not type times 10. I did not use the times 10 button. I used the EEXP. On some of your calculators, the EXP button will be you'll have a second button up here like a shift button, and EE will be one of the secondary functions. So you have to look for that on your calculator. All right, bottom line, 4.13 times 10 to the negative 7th. All right, now we want to know the frequency, so we're going to try and solve for this, and we know the wavelength because it says wavelength, so that's this guy right here. Wavelength is lambda. So I'm going to use this equation. C is equal to wavelength times frequency. So I plug in for C. I'm going to use 3.00 times 10 to the 8th meters per second. Wavelength we know is 4.13 times 10 to the negative 7th meters, and we don't know frequency, so we're going to solve for that. So you'll recognize from your math class, to solve for frequency, you divide both sides by the thing that's with the variable, so it'd be 4.13 times 10 to the negative 7th meters, divide by 4.13 times 10 to the negative 7th meters. All right, meters cancel on this side, as well as the 4.13 times 10 to the negative 7th, and I'll show you how to calculate this using your calculator. Remember, you do not use times 10, you use the EXP button. So we'd have 3 EXP to the 8th, or EE button. Remember, some of your calculators are you're going to have to hit second EE. Do not type times 10. So 3 times 10 to the 8th divided by Oh, by the way, you notice that when I did that, it changed into a number, but if you count the places, starting from here, 1, 2, 3, 4, 5, 6, 7, 8. It's 8 places, like it says. So that number divided by 4.13 exp negative 7th is 1.38 times 10 to the negative 15th, which means that I hit a wrong button because that's not the right answer. So I'm going to do it one more time. 3xp to the 8th divided by 4.13 exp negative 7th. There we go. So frequency is equal to 7.26. Now you know that your calculator gives you all these numbers, but they're not right. We've been studying significant figures and learning why they're not right. So you round off so that your answer has no more sig figs than the factor with the least, and that's 413. We're going to have 7.26, and then see that little elevated 14, that means times 10 to the 14th. On your calculators, it may say E14, and E means times 10. All right, now let's talk about the units. I'll show you the units over here. We have meters per second divided by meters. We got this number by taking this divided by that. So if you divide meters per second by meters, it's like saying meters over 1. When you divide fractions, you multiply by the reciprocal. So this is equal to meters per second times 1 over meters. So you flip the bottom and then multiply. So now meters cancel and I end up with 1 over seconds. So my unit is 1 over seconds. 1 over seconds is the same thing as a hertz, which is our unit of frequency. So you could say 7.26 times 10 to the 14th hertz. Now question number 9, number 8, I want to look at number 8. 8 says, what's the energy content of one quantum of the light in problem 6? So we just found the frequency of the light, 7.26 times 10 to the 14th hertz. So 7.26 times 10 to the 14th hertz. That was our frequency, so nu equals. And that's from problem 6. Now we're looking for energy. Well, the energy equation was E is equal to h nu. But now we're going to need to use this Planck's constant because that's what h is equal to. So we would write our equation, E equals h nu equals. H is Planck's constant, so it'd be 6.63 times 10 to the negative 34th joules per hertz. The frequency we know from right here, that's from problem 6, that was our answer to problem 6, is 7.26 times 10 to the 14th hertz. So now you notice I've got hertz on the bottom, hertz on the top. They cancel, just like our dimensional analysis cancellations did. And then to do the math, 6.63 exp EE, do not type times 10, so I'm going to use exp on this calculator. Exp negative 34 multiplied by 7.26 exp 14 equals 4.81 times 10 to the negative 19th, and the unit will be joules because hertz canceled. So that's the answer to number 8. All right, and there's my answer. All these numbers on the side are answers. All right, so now I want to take a look at number 4. I'm not going to do number 4, but I'm going to talk you through number 4. So in this equation, in this problem, we're looking for energy. So the problem says, what is the energy? And we're given a wavelength. The two equations are C is equal to wavelength times frequency, and energy is equal to h times frequency. So there are two ways that you could approach this problem. Since you're given the wavelength, you could plug that wavelength in here, except that, of course, since that's in nanometers, you would need to change it to meters, like I demonstrated for you earlier in this video. Okay, you could put wavelength in there, and then you could solve for frequency, because you know what C is. So you know this, solve for that. Then take that answer and plug it in there. You know what H is. So take the answer from here, multiply by H, and you'll have the energy. So that's one way to do it. Another way to do it is if you know that C is equal to wavelength times frequency, you could rearrange this equation to figure out what frequency is. So we could say that if we divided both sides by wavelength, that C divided by wavelength is the same thing as frequency, because over here they'd cancel out. So then you could have this equation, energy is equal to H times frequency, but we just found that frequency is the same thing as C divided by lambda. So you can plug that in, and now you've got an equation to find energy if you're given wavelength. So E is equal to Planck's constant times the speed of light and divided by the wavelength. All right, so there's two ways to do number 4. You could solve for frequency and get a numerical answer here, then put that numerical answer in here and solve for energy. Or you could rearrange the equation like this. Now you've got an equation, you know what H is, you know what C is, you know wavelength, and solve for E. Remember that wavelength must be in meters. You have to change nanometers to meters. All right, so our goal is to try and get every problem done on this problem set except for number 5, and we'll talk about number 5 on Tuesday.